So in case of the course on electromagnetic field theory and transmission lines, we have started with module 1, that is electrostatics. I already told about the idea of uh, the electrostatics. That is, we are going to describe uh, the field due to charges and charge due to or charge uh, which are exerting the field distribution and how to calculate one from another. That is what we have discussed in two different methods. One is using the Coulomb's law method, another one is the Gauss law method. So these two methods, whichever you feel easy, you can utilize them for understanding each other. So now, after calculating this electric field or charge distribution, now we have to utilize this for some applications. So for that, we supposed to extend this idea into the next dimensions that we are going to study the energy expended by the charges while it is moving from one place to another place. So that is what we are going to discuss over the class, and that we are going to reflect in some structures, let's say capacitors or inductors, we can easily apply, and that is what we are going to see in the next class using this Poisson and Laplace equations for analyzing the capacitance. That is what we are going to see in the next class. So today we are going to see the potential or the potential energy is the main topic for today's session. The Coulomb's law, I believe you people now thorough with that. So always you should remember while explaining the Coulomb's law, the uh, means we supposed to define what is a source charge, what is test charge, and the arrow mark always going from source charge to test charge, and which we call as a line joining. And in order to calculate this R vector, we supposed to subtract the vector which defines the with respect to the origin or from this source. So this R minus R dash will give us the R vector, and that is what's supposed to be utilized to define the force due to the uh, source charge upon uh, the test charge. Okay, so this we can do for multiple charges all the way. So we have to do vectorial addition. So this practice is very important. And next, we have studied about the electric field due to the charge, or for different charge distribution. We have seen that for different types of charge distribution. Then we move to electric flux. So the electric flux is the alternate definition for the field. So before describing the field, so people have started to explaining this field in terms of the displacement flux, which actually carry the charge from one place to another place, and it is giving opposite polarity all the way. So that is what which describe means describing the electric flux. But later people have pointed out both are one another same. They are actually uh, they are uh, they are the representation of same behavior of the nature in two different form. While electric field is independent of the material system. Here you can see that this we have to multiply this epsilon naught with E in order to get this. So the flux density highly relevant with the material property of a system. So for instance, if we put some dielectric material with a dielectric constant of epsilon r, then we have to multiply epsilon r here. So that what will therefore the flux density will increase. For instance, if the flux epsilon r is greater than the epsilon r is greater than 1, then which means it is other than the vacuum. For instance, many people think that the air medium will be having epsilon r of 1, but in this is Earth's surface, and at up to a particular height, up to I think up to 60 feet, this epsilon r is equal to 1.009. And when it is go on up, then in the outer surface, outer atmosphere, that is which we call space, which is about 10,000 kilometers. After that only we have the real what is called space, and you can float here easily. But till then, the gravity will be highly controlling you. At this place only we have epsilon r equal to 1. So This means that this here our air medium is exaggerating the field distribution, and by the way, we'll get denser flux lines. So the medium defines the properties of the flux density. So this is a minor difference between the flux density and the electric field. And the Gauss law, again, which is a very useful one to describe the flux density. Thereby, we can easily calculate the electric field. So while Coulomb's law defines from charge to electric field, the Gauss law in opposites, it can give this electric field to charge density. So both can be used in appropriate way, depends on the application, depends on the coordinate system, depends on the complexity of the problem, we can utilize that. So many people sometimes use this uh, uh, for we have to define step by step manner. I already discussed about in the last class itself. So now we have come to the next very important topic in the so-called in the electrical engineering itself. This is a very important point that which we call electrical energy. So what is electrical energy is simply nothing but whenever you try to move a particular point, a particular charged body or a point charge itself in the field. Okay. So assume that there is a point charge available at this particular point A, which is having a charge of. So according to this, it is a test charge. So this test charge is actually supposed to move from A to B. Instead of going in a straight line, it is taking multiple paths and reaching this point B. Okay. And then therefore, there is an external force applied on that to move from here to here. Meanwhile, due to this electric field, uh, it may be attracted or repelled, and by there, the force, the total force required to move this point charge from A to B, we can calculate using this simple expression, which is again the Coulomb's law itself. Okay, so the very first Coulomb's law which we have seen, so that is what it is again used here, where this E is nothing but the electric field due to some other source charge. Here some other source charge is available, my small q. So this is going to give the electric field. So that is nothing but q divided by 4 pi epsilon naught r square. So with respect to this, the electric fields are generated, and uh, that is going to exert the force on the q. Okay. And in order to calculate the total energy required, or the total work done or the total energy required in order to move this point charge from A to B, uh, uh, we have multiple paths, so it is the best way to calculate over a small length. So we are going to calculate over a small length, and anyway, this is going to be vectorial one because this is going to define a direction. So this dl vector is supposed to be calculated, and by multiplying this force, then you will get the small work done. The small work done will be calculated. So this is scalar one. So for this, we have to take the dot product of this force due to the source charge, which is somewhere else, which is defined in terms of electric field. So that is what, and over a small length we are going to calculate. So that will give a small work done or small energy expended by displacing the uh, charge from here to here over a small length. So force into dl. This negative sign always indicate that the force or the work done by external body. Actually, let's say that we are physically moving from here to here like that. So some external agent or some external force is used to move it. So that is what the negative sign indicate. And this the force actually we have expanded with uh, E QE, where this two are vectors, and when we multiply this, we will get uh, the resulting scalar quantity will come. When we multiply with that, we will get the work done. So this is, and now we have to integrate this entire thing from A to B. And the advantage of this particular method is we can integrate about a number of times, because from here I assume that I am dividing this as C, point C, then point D, like that. Then I can calculate from A to C, C to D, d to b, like that. Three integrations I can perform. And by the however, always the force of total work done will be same. So from point A to B, the total work done, if you take even n number of path, if you take some kind of curved path or some kind of zigzag path, if you take and reach this point B, all the way the total work done will be same with respect to the electric field present over the region. And so finally we can calculate the total work done by this. So this is actually very useful one. Using this particular expression only, we can calculate the total energy required in order to move a coil. For instance, we have a magnet, north and south. So we have a magnetic flux will be available. And then if we place a current carrying conductor, how this is going to rotate. So this similar calculations can be done with this type of calculation only we are going to use. Here it is done with magnetic, here it is electric field. That's a minor difference. But otherwise the idea is going to be very similar. So, and once you calculated the electrical energy, then we can easily say that how much mechanical energy we supposed to give in order to generate the current, or if we give this much electric field, how much mechanical energy we can get out of that, so which can be calculated in horsepower or something else like that. So this is the basic theory. We are going to expand it for some tricky applications like motor, generator, transformer, like that in future. So here we have the electrical energy. So this once you calculated this total energy, then we can define the potential all the way using this similar expression. So let's calculate for example I1. So what we are going to do, we are going to take a infinite line. So if we take an infinite line which is having a charge distribution of rho L, and therefore we can easily say that the electric field which is exerted by the this infinite line, we already calculated even with two Coulomb's law as well as Gauss law, both case we got the same expression, that rho L divided by 2 pi epsilon naught rho divided by a rho vector, okay, this unit vector. So this is the field expression. Now what is the meaning of that? If you take a infinite line, the field will be exerted out in all directions in as a vectorial, as a radical component. This arrow vector going to be there. And what about the z direction and the phi direction? There is no field component available. So that is what the meaning out of that. Now we are going to take a charge, and this charge actually available at a distance of rho from the line charge. So we are seeing from the top. Okay, so if we are seeing from the top and at the distance of rho, and this is the charge q which is available here. Now if you want to move this charge just around the line, then what about the total amount of energy required for that? So we are going to utilize this calculation. So we already know the electric field expression. If we calculate this dl vector, then we have to take the dot product. Then we have to go from one point to another point, then multiply with the charge value. That's all. Then you will get the work done. So for this, we are going to take a small length. The small length dl can be represented as a dl vector is nothing but rho dl. This is the length, and this is the corresponding unit vector. So this dl vector, we have this electric field. We are going to take the dot product of that. So when you take the dot product of this dl and this e vector, we can see that as of now we forget the magnitude. First we have to multiply these unit vectors. So this is a rho vector, this is a phi vector. Both are orthogonal to each other. And according to the theory of dot product, then we will get the result of 0. So no matter what about the magnitude, it is going to be 0. So by this way, we will get the dot product of this will be 0, and therefore the integration will become 0. In other words, the work done by the charge, in order to move around the line charge, in a radical manner. So then there is no work done by that. Okay, this is because the moment of the charge is perpendicular to the moment of the charge is just perpendicular to the field. Okay, this is very similar to that of how this Earth revolves around. So according to the gravitational field, there is no great change will be happening upon that. So only this acceleration alone going to change on the Earth, and that is why actually even this many years the Earth is actually simply revolving around that. And if it takes some other slight direction change, so then obviously the Earth will go inside the sun very quickly within about 8 or 9 minutes itself. So that much fast it will go and hit the sun. So this is what when the charge is actually moving from moving just around the line charge. If it is moving in the radical direction, okay, so which is actually going out of that. So then here the point A is here, point B is here, and for this particular line we have to calculate this dl vector. So this dl vector is very easy. This is simply going to be d rho. So this dl vector nothing but d rho into a rho vector. Now we know the electric field expression. We are going to take the dot product. Since here also we have a rho vector, here also we have the a rho vector, the multiplication will be non-zero value. Then we have to simply integrate over that. So we have taken the magnitude of the electric field and the magnitude of the dl, and this a rho component will be removed because both are multiplied, and we will get unit 1 and the q is here. So we have to just integrate from a to b, and if the positions clearly known, then we can easily do that. This is applicable to everywhere. Okay, so from just around that any place from a to b, whenever it moves, then the work done will be same because the electric field is same around all directions of the line vector. So this is how we have to calculate the force, the force as well as the work done by a test charge, capital Q, when it is moving around. Or so the same thing you can apply for a sheet, a infinite sheet. So if it is an infinite sheet, we know that the electric field is going to be. Can anyone say what is the electric field if the surface charge density is rho s? So what is the electric field expression? Let's say this is actually in the XY plane. Can anybody say that? What about the expression for the electric field if it is an infinite sheet charge? Remember, it won't be at any particular point, it will be same. So what is the value? Rho s divided by 2 epsilon naught az vector. Okay. It can be represented as an vector, which is normal to the surface. Okay. So in that case, the work done. So here also electric field is same. Here also electric field is same. Here also electric field is same. So when the charge is moving in the upward direction, then we are actually going to integrate over the electric field. So this will be integrated, which means that the work done will keep on increase. So that is what the interesting fact. This will go with respect to the distance from A to B. Let's say this value is L, total length, or it is going in a line vector length of L. Then the integration will give length L itself. So it is going to be linearly proportional. Okay. But in case of the line vector, since the rho is coming into the picture, you will get this integration of this rho in the denominator. So you'll be getting different work done. So these are the things you have to keep in mind while you work on the different charge distributions. So the line vector or volume integration or point charge. So they are going to give different different work done for a point charge when it is moving around that. And this work done, once you calculate it, then if you divide by the test charge value, then immediately we can get the potential or the potential energy. this potential, or most commonly referred as potential difference. So this is going to tell the work done per unit charge when the test charge is moving from one place to another place. Let's say there is a point charge available, and because of this point charge Q, the electric field exerted in all directions, we can easily say that it is going to be Q by 4 pi epsilon r square AR vector. Okay, and now due to this electric field, we can easily calculate the work done when we move a particular charge from point A to B. So work done we will calculate, and we are going to divide by that. So which is nothing but the integration of all the electric field with respect to the line particular line vector, this from A to B. So we are going to take a small dl vector, and we are going to calculate that from A to B, and that is what the potential acquired, or the potential energy acquired by the charge when it is moving from A to B. Okay, and due to the presence of the electric field E, and this is often represented by V, which we call most of the time as potential difference. So potential difference from A to B is negative sign for B to A, but otherwise the magnitude will be same. So that is what uh, often representing this. So this is what the same potential which we are actually saying as a volts in the electrical engineering. So this is here where the very first time the potential is defined. You should remember the current has not yet come. So the current will come in the next chapter. So this voltage or the volts which defines the potential energy or potential difference between two different places due to the presence of electric field, which will define the total work done required to move the particular test charge from point A to B. And this is a very important calculation supposed to be done. And because of that, in future, so many applications going to come. Now, assume that we are having a particular point charge, and that is going to exert the electric field of E. And let's say this is available here. And now what we are going to do, we are going to calculate the electric field at this particular point, electric field at this particular point. Now, if we find the line joining between that, then if you multiply that, then you will get the total work done required. So that is what we are going to do. So we know the electric field. This dl we have to calculate. This dl vector is nothing but the small dl vector is nothing but the r vector. So here it is the r vector. This r vector can be calculated as difference between this rb vector minus RA vector. If you know the exact locations, you can find the difference between them. That is nothing but R vector. And we are going to calculate this dr vector. So this dr vector depends on if it is having x, y, z axis, accordingly it will be coming into the picture. And so we are taking this dr vector and AR vector, and this also AR vector. So both are going to multiply each other, will result unit 1. And therefore we will get it. So this dr is nothing but the difference between these two, A to B. So that is what it is described over here. And there comes the potential difference. So we will be having the potential at point B and potential at point A. When we find the difference between that, then you will get the potential difference between the 2 points due to the electric field from the point charge. So in many times, actually, we will always call this point A as the reference potential, and this reference potential sometimes will be called as surface potential. So assume that there is a surface, and this surface is having a point. It is having a at this with respect to a reference point or something. Let's say this is the point B, and this is always the same distance. And here the potential is A, and here the potential is B. Now we will always calculate that. And in many places, this value will be 0, which we call ground plane or something. So with respect to the ground plane, what about the potential at this particular point due to the point which is going to give the electric field all over the place. And this reference one, if we consider it is located at a distance of infinite, let this R or RA point is almost infinite, then according to that, if we put 1 by infinite, you will get 0. Then this VA will become 0. So this is why we always consider this reference plane or the reference potential is equal to 0, which in other words, the meaning is we are actually going to bring this electric field, sorry, the test charge from an infinite place to this particular point. So for this, the total work done will be equal to the VB, because VA is equal to 0. So VAB is equal to something but VB, which we can define like this. And this R here, R is equal to RP, which means the point where we have the finite distance from the test charge itself. So that is what we can say that is the potential at this particular. So in other words, we can say that we need not to calculate the potential difference or something like that. We can directly calculate the electric field at every point. And once we calculate the electric field at every point, then we can calculate the so like how we calculate the electric field at every point, we can calculate the potential at every point without having the second reference point, and otherwise we can assume the reference point is available at infinite location. Therefore, the corresponding potential is 0. So if we have a test charge Q here, then the electric field at this particular point, let's say this distance is R, and whenever it is very close, we already know that the electric field is very high. E1 is high and E2, which is at this particular point, is little low, and it is keep on go. And at when it is at infinite, the electric field is going to be 0. And similarly, the potential here also it is equal to 0, and there it is keep on going to be very high near to this. So if there is a charged body, exactly at the surface of the charged body, we will get the potential is very, very high. And if we move away from the charged body, then the potential will be less, and therefore the work done or the work done required to move within that range will be less compared to the nearer. So these are the key things we have to note down while we consider the potential due to the electric field. In other words, we call electric potential. And we can calculate the electric potential very similar to that of electric field due to multiple charges. So if we have multiple charges, then we are going to assume the reference point is somewhere else. It is going to be available at infinite. Therefore, it is enough to calculate from the origin point to this vector, and there comes the total potential. So the total potential is nothing but sum of all the potential due to the multiple charges at that particular point. Or so assume that there are multiple points are available, and this particular point P we have to calculate. So we have to find the line joining between all these source charge Q1, Q2, Q3 all the way. And at this particular point, we have to calculate the total electric field. And this total electric field, the important thing is we have to calculate the DL for all the vector, and we have to multiply. Then only we will get the work done. From there, when we divide the Q, we will get the electric field. So indirectly, what we are doing, we have to calculate this denominators. And with respect to this charge Q, we are calculating this expression. There comes the total potential. So, and so the very same as that of this multiple point charges or multiple discrete point charges, we can also have continuous charges for different cases, line charge or surface charge or volume charge. We can use the very same expression here. If it is a line charge, then we have to take a small length. So if it is a line charge, let's say, and we are going to take a small dl length, and because of that, at this particular point, what is the potential? Then we have to integrate over the space, integrate over the length. We have to calculate. So that is what it is shown here. Same thing for this surface and this volume. And here this dl is going to be infinitely small, and when this tend to 0, it will be act like a point charge, and we are going to integrate multiple point charge over this length, and that is what indirectly it means. You people can easily understand that. And the next very important understanding what we have to keep in mind is when we are having a loop of path. So here you can see there are 2 point charges. One is point A and point B, and a charge. Let's say the charge is Q, and this Q is moved from A to B. Again, it is moving in another path to A. And we already know that the work done from this A to B, if it is W, then from B to A also the work done will be W. Here, these two are scalar quantity. But the moment we introduce this, the concept of electric field, then the potential difference will come. Then in that case, due to this W, the potential work done VB, VAB, and because of this path, you will get VBA, which is nothing but minus of VAB. Then what about the total work done? This work done is positive W, this work done is negative W, which means actually we are actually moving outward from the electric field. We are moving inward from the electric field once again. That is the indirect meaning. When you add both of them, then the total work done will be 0, or the total potential difference will become 0. Okay, so in other words, we can say that if we are having electric field distribution and a particular point charge is moving in a closed loop, okay, in a closed loop, then obviously the total potential difference will become 0. This is same as that of how we define a closed path in a circuit theory, that this is going to be having V1 vector, this V2 and V3, and this is the total. So when you add all of them, we're supposed to get the value of 0. So that is the closed path integration. So to define that, we always add circle in the integration symbol. And so this is what the important result we are seeing here. And now we are going to apply the Stokes theorem. The Stokes theorem, we have to remember the previous one which we have seen is divergence theorem, which tells that the integration over the surface can be done with integration over the value. Similarly, a closed surface integration can become volume integration. Similarly, a closed line integration can be calculated by the surface integration. So that is what the, and in that case, we have to take the curl of the particular vector. So this is the vector of interest. So we are going to calculate this curl for that. Take the dot product with the ds vector. So that is what the Stokes theorem tells all about. So if this is so, then in order to calculate this line integration, we can take curl of that with respect to the surface integration, which is equal to 0. Okay. In other words, this ds cannot be 0 because it is small but not equal to 0, and the integration of the surface also is not going to be 0, and therefore this del cross E is supposed to be 0. So that is what it is described over here, which is the second Maxwell's equation. So del cross E equal to 0. In other words, we can say that the electric field is conservative. Conservative means it is always having a origin, and it neither can be created nor can be destroyed. So in other words, it is having a origin point of from a particular charge, and it cannot be looped like a magnetic field, how it can be looped in a single structure itself. Let's say you have a magnet north and south, we generally loop it with the magnetic field, but such a loop cannot be done, which is completely meaningless in terms of electric field. In case of electric field, there should be a two distinct locations of positive and negative. There comes the electric field will come. Okay, so that is what the two meaning, like conservative and the irrotational. So we can simply say that the electric field is a irrotational vector, and there comes del cross E equal to 0. On the other hand, del dot E will not be equal to 0 because it is conservative. So this is the important properties of the electric field, electric flux, electric potential. So these are the things we have to keep in mind. Let us calculate with some numerical insight. So assume there are 2 point charges. Okay, these 2 point charges, minus 4 microcoulomb and 5 microcoulomb, 2 point charges located at these 2 points. And so we can call these 2 points as, let's say, A and B. And now we have to calculate the potential V at this particular point P, assuming the zero potential is available at infinite, which means we are bringing these 2 points. We are actually going to bring a test charge from an infinite point to this point P, while these 2 charges are presented at these 2 locations. So what is the meaning of that? We have point A, point B. Here we have Q1, Q2. So these are nothing but Q1 and Q2, and they are actually going to exert the electric field. At this particular point, they will be vectorially adding each other from an infinite place. We are actually going to bring this point charge Q from here to here. At that time, we have to ask ourselves what is the total work done, and that total work done per this test charge is going to be potential, and so that is what we are going to calculate. So we have 2 source charges, and for this 2 source charges, we have to calculate the total potential at this particular point P. So how to calculate that? We have to find the line joining of these 2 vector, this R1 vector, and this is going to be R2 vector. And once we calculate that, we have to calculate the magnitude of them. So how to calculate this? We know this point value we know. We have to find the difference between that. So 1 minus 2, 0 minus 1, 1 minus 3, like that. When we calculate, we will get the R1 vector, and we have to take the magnitude of that. I believe you know about that. You have to take root of square of all the value, just to add them, and you will get the value. So similarly, we are going to do for R2 vector, find the difference between these 2 points and take magnitude for that. You will get the value of root of 26 here. And in general, there will be a extra potential due to the reference plane, but since we are actually bringing from infinite, this value is going to be 0. So just we have to calculate these 2 things. So we have calculated this magnitude of the R vectors, and Q values are known, and this epsilon naught value also known. And we know the epsilon naught is going to be 8.857 into 10 power minus 9 in general. But the most often value people generally use is by applying this pi as a irrational component. In fact, epsilon naught is also a irrational number, therefore which can be represented by 1 by 36 pi. This it is because here we have 4 pi. Here, if you put 36 pi, when we cancel, we will get the value of 9, which is very easy to do the multiplication or division. So at this particular point, 0, 0, 1, 1, 0, 1, the potential due to this both charges are going to be this. So this is the micro Coulomb, and this is 10 power. This is nothing but epsilon naught 4 pi. So when we cancel, we will get the value of 9, and 1 by 9 we can bring it to the numerator, and we have to take this calculation. At the end, we will get this value. This kilo is coming because when we divide this 2 value, you will get 10 power minus 3, 1 by 10 power minus 3, which will become 10 power plus 3. We will get this kilovolt. Okay, so this is the potential due to this 2 point charges available at 2 different places. And when we bring the test charge, as of now, the interesting part is this test charge value is not known at all. It may be 1 nanocoulomb, 1 kilocoulomb, whatever it may be, but the total work done will be same for this all. Let us take a small quiz, and some of you are going to help me to solve these quizzes. So there is an electric field which is actually uniform almost throughout the region, and there are 3 points are available. Now we have to calculate the potential difference between this points. So now first we are calculating the potential difference between this point A and B. So this VB minus VA. So what's supposed to be the value of it? Can anybody say that? You are given with 3 choices. So whether it will be greater than 0 or less than 0 or it will be equal to 0.
Equal to 0.
Can you say why?
Because they're in the same potential. We're traversing perpendicular to the electric field.
Okay.
So
So
E dot dl will become 0.
in other words, the line joining you're saying, is it?
Yes, sir.
Yeah, this line joining or which is having a small dl. So this vector is going to be perpendicular. So yeah, that is correct. There is another way we can define the same. This he has said mostly in mathematical way, in philosophical way. If there is a source charge which is available somewhere else, it is going to give the electric field, uniform electric field over the space. And with respect to this particular point, A and B are going to be at the same location, okay, at least with respect to the this source charge. Therefore, here potential A will be equal to potential B. The difference will become 0. So in this way also we can explain, but I appreciate the first explanation is more precise than this physical one. Sorry, the philosophical one. So yeah, the point A and B relatively say located at the same distance. But what about this A, C and AB? What about the potential difference? Will be greater than or less than? What is the opinion for that? What about the potential difference between these 2 points? Let's say we are going to calculate VCB, which is nothing but VC minus VB. So whether it will be positive or negative. So which VC will be greater or VB will be greater? You think the example what I told here. So according to this simple thing, as the R is in the denominator. So if you go far away, the potential will become lesser and lesser. So VC will be less than VB. That's what the value will be less than that. Should remember that. So for this particular problem, it is answer A. And now the second question, the point C is at a higher potential than point A. So that is what
False.
yeah, it is a false one. So with respect to the direction of the electric field, always potential will be decreasing. In this question, please read and tell. So here you have the question. If a negative charge is moving from point A to B, what about the electric potential energy? Whether it will be increasing or decreasing or does not change.
Does not change, right?
So why it won't change?
So because it is moving in the same potential.
Yeah, B already they possess same potential. Therefore, there is no potential difference. So the potential, the work done is nothing but the Q into B, BAB, or the difference between that. That is going to be that this already 0. Then this work done supposed to be 0. In other words, the potential energy will not be changing. So what about this particular one?
VSC is equals to VBC.
Easy. Okay. Yeah. So I believe you people have understood the concept of potential. So it starts with work done. So let's say a point charge is moving from one place to another place in presence of electric field. Assume that your room is there is a room, and in two sides of the room, one side we have a positive plate, and another side we have negative plate. We can call them as anode and cathode, and they are very big. Okay, so when we give when we apply when we connect with the battery, then from negative cathode to positive, the electric field will go. Okay, so in that case, all of them will be in straight line. Assume that someone is carrying a charged body from one side of the room to other side of the room. So let me draw that. So we have a room. So this side we have anode, and this side we have cathode. Both are connected by a battery, very big battery. This 10,000 volt battery. Okay, so 10,000 volt battery. So the electric field will be like this from cathode to anode. It will be uniform throughout, and someone is carrying a negative charge, let's say some negative Q charged body, let's say it may be a mobile phone or something else. When they carry from here to here, when they move on, they will be experiencing a force acting upon this charged body. Sometimes this charged body entirely it may move out. So, or it may be dispersed. So this is what happening inside the microwave oven. So inside microwave oven, we have two plates. Both are connected with a oscillating volt. So here this V is nothing but V naught. Let's say sine omega t. This omega, can anybody say what is the expansion for that omega? No idea about that. What is this omega? That is 2 pi f, where f is nothing but the frequency. This frequency will be in gigahertz, which we call microwave. So this microwave signal is going to travel on this. And when we place some dish, okay, let's say some popcorn or some dish we are actually. So in this, when we zoom this atomic level, we will be having water. So H2O will be polarized in this way. So one is positive charge, negative charge separated by a distance, and they will be experiencing this potential difference, and there come they supposed to make it zero. They will do the work, and so they will tend to move. So since it is going upside down, so whenever it is up, it will be in this way, it will be oriented. When it is negative off cycle, it will be oriented in the opposite way. So when they are actually moving in the very fast way, so let's say this is the cone, and we have water molecule everywhere, and this water molecule going to rotate, and they will be spinning at very high fast velocity because the frequency is very high. So you just imagine there is a some wheel is rotating in the velocity of about gigahertz. So they will be simply popped out, and they will be breaking the molecules of the corn, and they pop out. That is what you are calling as popcorn. So that is actually happening because of the simple phenomena of the potential difference. We will study in detail because the material physics will come into the picture. There comes some interesting behavior can be studied. And I believe we can study this potential gradient in the next class. Okay, we will stop here. And if you have any questions on this regard, you can ask.